This is section 4.9. In this section, we're going to be talking about mechanical vibrations, so some more real-world problems. So we have a function we're provided for external force in a mass spring system. So that is the external force is equal to inertia times the second derivative of y with respect to t, plus damping, plus the first derivative of y with respect to t, plus stiffness times y. So we can write this as such, with m representing inertia, b representing damping, and k representing the stiffness. We are first going to focus on the undamped and free case. So undamped means this damping constant is just 0, and free means there is 0 external force. So this greatly simplifies things. We're now just looking at 0 is equal to our inertia times the second derivative of y, plus the stiffness times y. Finally, we're going to divide by that leading m and perform a substitution. Omega is equal to the square root of k over m. So this gives us the form 0 is equal to the second derivative of y with respect to t plus omega squared y. And omega is just a constant. We don't have to think of that as another variable because k and m are the stiffness constant and the inertia constant that are provided in the equation. So note that the auxiliary equation r squared plus omega squared will always have complex roots, and they will be plus or minus omega I. So as we talked about before, I think in section 4.3, a general solution to this equation is y equals some constant times cos omega t plus some constant times sine omega t. Now we have a trig identity that can simplify this. And by simplify, I mean take out the cos entirely and just write it in terms of sine. So sine of at plus b is equal to this right here, sine at cos b plus cos at sine b. So if we let c1, that constant, be some constant a times sine of another constant phi. So we're introducing two new constants here, a and phi. And we don't know what they're equal to yet. But if we perform these two substitutions, then we can make y look like the form that we want, sine phi times cos omega t plus a cos phi sine omega t. It's now in the proper form to use this trig identity. So we can simplify it simply as y equals a sine omega t plus phi. And this is the equation we're going to work with moving forward. So we can further play with this to try to determine what exactly phi and a are. So let's scroll back for a moment and recall that c1 is equal to a sine theta and c2 is equal to a cos theta. So rearranging those equations, we get a is equal to c1 over sine theta, but a is also c2 over cos theta. So that means these two are equal to each other. And that means that c1 over c2 is equal to tan, I may have been saying theta, it's actually a phi. So it's c1 over c2 is equal to tan phi. In addition, we have c1 squared plus c2 squared is a squared sine squared plus a squared cos squared. Well, factoring out the a squared, we know that sine squared phi plus cos squared phi is just equal to 1. That's another of our trig identities. So we're left with c1 squared plus c2 squared is equal to just a squared. So to isolate a is the square root of c1 squared plus c2 squared. Now we can't go too far with this because it would be incorrect to say that phi is simply the arctangent of c1 over c2, because arctangent is bounded between negative pi over 2 and pi over 2. If we picture that on our unit circle, arctan is only on this right side of the circle. But it's possible, depending on if we have some negative numbers involved, that the angle we're measuring is actually somewhere on the left side. So we can't simply say that it's just the arctangent. We're going to need a bit more information. Okay, this identity shows us that the motion of mass in an undamped free system is a sine wave, also known as simple harmonic motion. So this is fairly simple. The fact that what we have can be broken down into just a sine wave, because if you'll look back, that's all we have here. It's some constant times sine of something else, some variable. It's a constant omega times our variable t plus another constant. The constant A is the amplitude of the motion. Phi is the phase angle. The motion is periodic with period 2 pi over omega and has natural frequency omega over 2 pi, just the inverse of the period. The constant omega is the angular frequency. And then when we talk about our units, that means omega is measured in radians per second. Omega over 2 pi is measured in cycles per second. And 2 pi over omega is just measured in seconds. As you'll recall, that makes sense because radians is unitless. So omega is measured in 1 over seconds. That's radians over per second. So if we flip that over and we get our 2 pi over omega, we're now just measuring in 1 over s, which is just seconds. Okay, now we're going to take all of our, well, before that, we'll mention that there's a lot of physics terminology here that will be very useful for when you're solving your real world problems, and it will certainly be useful in your physics classes and your other engineering classes moving forward. We're mostly going to be worried about the mathematics here. So don't expect a question on your final exam of what is the natural frequency, or give me a detailed explanation of what the phase angle is. We are just going to try to stick to the math here. So example 1, a mass of 500 grams is attached to a spring of stiffness K equals 8 newtons per meter. The mass is displaced 500 centimeters to the right of the equilibrium point and given an outward velocity to the right of 2 meters per second. Neglecting any damping or external forces that may be present, so that is our Fext and our B value. So that makes this an undamped free equation we're going to be dealing with. Determine the equation of the motion of the mass along with its amplitude, period, and natural frequency, which we just discussed. How long after release does the mass pass through the equilibrium position? This could be a question mark. There we go. Okay, because we have no damping or external forces, we will use the equation 0 is equal to the second derivative of y with respect to t plus omega squared y. Before any further calculations, we must convert to proper units, because you'll notice this question is a little tricky. It deals with grams and centimeters when that's not really our standard. In particular, we do not generally use centimeters and grams, but rather meters and kilograms. So also, we'll scroll back up and see, why is this so important? Well, this is measured in meters per second, and this is measured in newtons per meter. So it becomes very important that everything be measured in our standard with meters and kilograms. So 500 grams becomes 0.5 kilograms, and 500 centimeters becomes 5 meters. The angular frequency, omega, is the square root of k over m. Well, k, that's our stiffness constant. M is how much the position has been shifted. So that is the mass is displaced 500 centimeters, which we just showed to be, oh, sorry, no, mass is, M is mass. Okay, strike that. M is mass, not meters, of course, because when it's a variable, it's referring to mass. So, or a constant in this case. So the mass is 500 grams, which we just showed to be half a kilogram. Perfect. So 8 divided by a half is 16. Square root of 16 is 4. And as we know, angular frequency is measured in radians per second. So substituting this value into our general solution, we get y is equal to c1 cos 4t plus c2 sine 4t, because previously we had omegas in here, but now we know omega is equal to 4. Now we use our initial values. Y of 0 is equal to 5 and y prime of 0 is equal to 2. Let's go back to the question to see where we got this information from. The mass is displaced 500 centimeters. So you can think of that as your y value because it's how far we've actually moved the thing. And that's what y is measuring, is the position. So since it's been displaced 500 centimeters, that's 5 meters. So we'll say y0 is equal to 5. That's our initial position. And its outward velocity, of course, velocity is the derivative of position with respect to time, and that's equal to 2. So at time 0, we have y is equal to 5 and y prime is equal to 2. So this will give us our initial values. We plug in t is equal to 0. And when y is 0, we have it's equal to 5. So that means c1 is equal to 5. Note how this just disappears because sine of 0 is 0, but cos of 0 is 1. Now we'll take the derivative. That's a little bit of chain rule. So the 4's come out front. Cos becomes negative sine becomes positive cos. And then we plug in 0 again, but this time it's equal to 2 because we have that y prime of 0 is equal to 2. The sine falls apart because sine of 0 is 0, but we're left with this 4c2 here. So 4 times c2 is equal to 2. That means c2 is equal to a half. So our function y of t is equal to 5 cos 4t plus 1/2 sine 4t. But we want to put it in this notion, this way that has a and has phi. So we got to figure out what a is next. Well, a is just the square root of c1 squared plus c2 squared, as we showed before. So c1 is 5, c2 is a half. When you square them both, you get 25 1/4. And 25 plus 1/4 is the square root of 101 over 2. First, you get the square root of 101 over the square root of 4, but the square root of 4 is just 2. So that's how we get here. So we plug that in. So we now have our a value. We have our omega value. All that remains is phi. So tan of phi is equal to c1 over c2. And 5 divided by a half is just 10. Now we've got to do this whole arctangent thing about where does this angle actually lie such that its tangent is 10. Well, a, c1, and c2 are all positive. So that means that sine phi and cos phi are positive as well. And if sine phi and cos pi are both positive, then we're in quadrant 1. And since we're in quadrant 1, we can just take the arctangent. Because remember, the arctangent is anything that's in the right side of this. And the arctangent of 10 is 1.47 roughly. So to answer the question, amplitude is square root of 101 over 2. Phase angle is approximately 1.47. The period is pi over 2 because we take 2 pi and divide it by omega. And omega is equal to 4. That's pi over 2. Natural frequency is just the inverse. That's 2 over pi. And finally, the last question asked was finally to determine when the mass will pass through the equilibrium position y equals 0. We need to solve this equation when y of t is equal to 0. Well, we've got a product is equal to 0, and clearly the square root of 101 over 2 isn't equal to 0. So it must be the other piece, sine of 4t plus phi, that is equal to 0. So we get sine 4t plus phi equals 0. Now, when is sine of something equal to 0? Well, it's when the inside of that sign is equal to something times pi, some integer times pi. So we get that it's equal to n times pi for an integer n, but actually we can be more specific than that because we want to know the first time that it's going to pass through the equilibrium position, so we can set n equal to 1. So what we end up getting is that 4t plus phi is equal to pi. When we isolate t and we plug in that phi is known as being roughly 1.47, we get our solution that time is roughly 0.42 seconds. And that's our example. Okay, now we're going to move on to free vibrations in which the damping constant is not 0. So we're going to take some b values now that aren't 0. So we're still going to have it free, so the external force is 0, but now we have a b value in here. This auxiliary equation isn't as nice as the previous one. We have to use our quadratic formula, and these are our two solutions. Notice the plus or minus, so there's two solutions in there. We're going to break this into 3 cases, and it's our normal 3 cases for these quadratic expressions where we're looking at double roots, no roots, and single roots. So our first case is underdamped or oscillatory motion when b squared minus 4k is negative. So here you can think of this as having no roots, or more accurately, no real roots, because the roots of this auxiliary function are alpha plus or minus I beta, where alpha is negative b over 2m, and beta is 1 over 2m times the square root of 4mk minus b squared. This is, again, stuff we went over in section 4.3, talking about these complex roots. So hence, this is our general solution. Y of t is equal to e to the alpha t times c1 cos beta t plus c2 sine beta t. We're going to use the same trig identity that we used earlier in this video to put this in the form a e to the alpha t sine beta t plus some phi constant. We have the same equations from before. A is equal to the square root of c1 squared plus c2 squared. Tan of phi is equal to c1 over c2. So we can view y of t as the product of 2 factors. The damping factor. Notice how this a e to the negative b over 2mt, that b is in there. So that's got the damping constant in that. Multiplied by the sine factor. And this is just going to be something that waves in between positive and negative 1, because that's all a sine value does. Because the sine factor varies between negative 1 and 1, with a period of 2 pi over beta, the solution varies between negative a to the alpha t and positive a to the alpha t, with quasi-period 2 pi over beta. And then we know what beta is equal to. And quasi-frequency 1 over p. Now we use the word quasi because the damping effect means that the system is not truly periodic. So we'll just draw a graph of what this damping actually looks like. When we're looking at this position of this mass on a spring, since this is oscillatory motion and there's a damping factor, it's going to do something like that, where it's not actually a nice sine wave like we were looking at before. Since it's being damped over time, it's going to come toward the center. And to call it actually periodic wouldn't be correct. It is waving up and down over and under the x-axis, but the height is getting smaller and smaller. So we can't actually call it a period. So we call it a quasi-periodic motion and a quasi-frequency. Okay. Also, since B and M are defined to be positive, that's our damping constant and our inertia constant, we get that alpha, which is equal to negative b over 2m, must be a negative value. That means that the exponential factor tends to 0 as t tends to infinity. That's kind of our algebraic explanation of what I just showed graphically. And that's the end of this first case. Just gives us an idea of what the solutions look like and what the graph looks like. Our second case is overdamped motion, when b squared minus 4mk is positive and the auxiliary equation has two distinct real roots. So again, from our quadratic formula, we know what these two solutions look like. It's negative b over 2m plus 1 over 2m square root b squared minus 4mk. And then we also have the same thing where we put a negative sign in here. So the general solution is going to look different from when we had complex roots because these are real roots. So it's just c1 e to the r1t plus c2 e to the r2t. Now, here's something to think about. Are these roots positive or negative? Well, since b and m and k are defined to be positive, then this is clearly a positive value times a negative value minus another positive value, which is just going to give you a negative value. But what about R1? We have some negative value plus some positive value. So it's not immediately clear whether this is positive or negative, but we know that b is greater than the square root of b squared minus 4mk. Kind of roughly pitching that, it's because if you were to square both sides, you would get b squared is greater than b squared minus 4mk. Then you cancel out the b squareds and you just get 0 is greater than negative 4mk, which is clearly true because this is a negative value. So we get that since b is greater than the square root of b squared minus 4mk, this is also a negative value. So both solutions are negative. Therefore, as t tends to infinity, our solution y will tend to 0. Now we're going to find the critical points, supposing c1 and c2 are not both equal to 0. If c1 and c2 are both equal to 0, our solution is just y equals 0. So critical points, you have to take the derivative. And then we're going to try to simplify this derivative best we can. We're going to factor out an e to the r1t and set it equal to 0. Well, e to the r1t isn't equal to 0, so it must be the other factor that is equal to 0. And we solve for t. And we get a single solution. So there is one critical point. There is at most one local max or min. This makes for an interesting type of graph because we would picture something bouncing on a spring as going kind of like a sine wave, and it may peter out or it may go on forever. But we do picture it having several critical points. But the fact that we can only find one local max or min means it's going to look something like this, maybe. You'll actually see a number of possible graphs on page 216 that display the options for what such a graph may look like. Okay, our third case is critically damped motion. That's when b squared minus 4mk is equal to 0. And that means the auxiliary equation has a double root at negative b over 2m. Once again, from our work in sections 4.2, 4.3, 4.4, we know what this solution is going to look like then. It's y is equal to c1 times e to the negative b over 2mt plus c2 times t times e to the negative b over 2mt. This motion as t tends to infinity is actually going to require L'Hopital's rule. We want to know what this is going to happen as t tends to infinity. Is it going to tend to 0 like this case, or is it going to tend to nothing like this case? We're not sure yet. So the reason L'Hopital's rule is appropriate is because we have a quotient here where both the top and bottom are going to go to infinity as t goes to infinity. So if we take the derivative of the top and the bottom, we get that the top is constant, but the bottom, the denominator, is going to go to 0. Sorry, infinity, which means that the whole limit will go to 0. So next we'll do as before and find our critical points. So this is our y prime. Looks a bit messy because this negative b over 2m has to keep coming outside when we take the derivative of e to the negative b over 2m. times t. But we get this value in here being equal to 0, which is clearly just a single value. There's no squares or anything going on in there. So we get, again, at most one local max or min. So again, we're getting this strange type of motion where maybe it's doing something like that, where there really is just one critical point. We say this is non-oscillatory motion. Quite clearly from the graph, it's not oscillating. And if b were any smaller, oscillation would occur, because then we would be, if b were any smaller, we would be in one of the other two cases. We would be in the oscillatory case, which was our first one. Yeah, underdamped or oscillatory, there it is. Okay, let's go to our example. Example 2. Assume that the motion of a mass spring system with damping is governed by second derivative of y with respect to t plus b dy dt plus 9y is equal to 0. We have a couple initial values, y of 0 equals 1, y prime of 0 equals 0. We recall from the previous example what this would be in word form, where this y of 0 equals 1 represents how far the mass has been displaced initially, and y prime of 0 represents the velocity initially. Find the equation of motion for b is equal to 4. The auxiliary equation is r squared plus br plus 9 is equal to 0. And its roots are, as we discussed before, negative b over 2 plus or minus 1/2 square root b squared minus 36. Now we've been given that b is equal to 4, so we can plug that in. And you'll notice these negative values under the square roots. So that means we're looking at the first example with complex roots, the overdamped or oscillatory solutions. So we get our solutions are negative 2 plus root 5i and negative 2 minus root 5i. This is an underdamping, and the equation of motion has the form y of t is equal to c1 e to the negative 2t cos root 5t plus c2 e to the negative 2t sine root 5t. Well, let's use our initial values. So when we plug in y of 0 as before, that just gives us c1. So c1 is equal to 1. This derivative, there's a couple of product rules going on, so we get a lot of terms. But luckily, we get to plug in 0 for t. So these sine ones are just going to disappear. And these e to the 2t's, well, they just become e to the 0. So that's 1. So all we're left with is negative 2 times c1 plus 5 times c2. We decided that this initial velocity was 0, so we get that c2 is equal to 2 over root 5. Now a is equal to the square root of c1 squared plus c2 squared. So c1 is 1, c2 is 2 over root 5. So when we square those two values, we get 1 plus 4 over 5. Take that square root. Well, 1 is the same as 5 over 5. So 5 over 5 plus 4 over 5 is 9 over 5. Take the square root of that. Square root of 9 is just 3. And square root of 5 will stay as the square root of 5. So that's our a value. And then the last thing we're going to need is phi. Well, tan of phi is c1 over c2. So that's root 5 over 2. And we want to figure out, can we just use arctan? What can we do here? Well, since a, c1, and c2 are positive, that means both sine and cos are positive. And that means we're in the first quadrant, which means it is appropriate to take the arctan as our solution. So phi is equal to the arctan of root 5 over 2, which is approximately 0.85.